Yeah, so for the midterm, I think some of you did it pretty well. And what we are doing is actually some pretty fundamental thing. But so that's why I want you to able to understand all my the solution, right? Please go back to review it. Make sure that you understand everything. The first one is simple, right? The first one, what I'm asking here, right, is that what is the inner product between A and B? The only thing that is tricky is that the A is in the bra. So you need to do the transpose, right? So first it becomes this transpose. And then you need to apply complex conjugate to it. So some of you forgot to do that. So it becomes negative 3i because this is purely imaginary. And then negative 2i becomes 2i. Make sense? And then in terms of the and then for B is still 2202i. And then in terms of the calculation, just do matrix multiplication. Negative 3i times 2 becomes negative 6i. 0 times 2 is 0. 5 times 0 is 0. And then 2i times 2i is what? Negative 4. Right? So be very careful. I times I equal to negative 4. Now, then I ask you to find B inner product with A, which you can just use this equation, right? Because B, as a way to memorize it is B inner product with A is a scalar. So then if you swap it, you must take the complex conjugate, right? So complex conjugate of this guy is the real part negative 4, you do nothing. The imaginary part, you put a negative to it. So then you get this. So this is very fundamental. Unfortunately, I see not everyone did it right. So please check your solution. Make sure that you did it right. Then for B part, about the normalization, about normalize B, right? How do you normalize it? Right? I hope you realize that when we write B as this one, what do we mean? We mean B, right, equals to 2, maybe 0, 0, because this is a 2 qubit. It has 4 basis states, plus 2, 0, 1, plus 0, 1, 0, plus 2i, 1, 1. Do you understand what I'm writing here? For B, right? So that's why you normalize with all the coefficient. 2 square, 2 square, 2i squared. Remember, take the magnitude, not just square. Some of you give me negative 4. No, we take the magnitude and then the square. So this is 4. That's why you have 12, 1 over square root 12. 1 over square root 12 is 1 over 2 times square root 3, right? So you cancel the 2, you get 1 over square root 3. Yeah, no, not just negative. This is the magnitude. Magnitude of 2i is 2, right? Magnitude. Okay? So, but some people just do 2i squared. Then they get negative 4. Okay? So, and then a question is asked after this normalization, right? What is the probability of getting 0, 1 in a 2 qubit measurement? Then, of course, it is just the coefficient for 0, 1. Again, this is 0, 0. This is 0, 1, right? This is 1, 0. This is 1, 1. So 0, 0 has 1 here, but you scale by 1 over square root 3. So its square is 1 over 3. Any questions? And not many people got this right either. I mean, not all people got this right either, right? So really try to think about that, right? So that C is free. Now, then what if we, instead of doing this measurement, right, not performing step C, what if the space is 2 qubit and now we only do one single qubit measurement? We only do one single qubit measurement for the least significant bit, right? It's the little endian, but using little endian. Again, here I show you that 000111011. So what we are measuring is the second one, which is 01, and then the fourth one, 11, right? So both of them has a probability of 1/3. Now maybe a little bit messy, right? Do you see that? We have, this is 1, this is I. Both of them scaled by 1/√3, right? So their magnitude is 1. Again, not I squared, it's magnitude of I squared. Okay, so that's why you get 1/3, 2/3, because you can get 0, 1, or 1, 1 if you only measure the last qubit, right? For E, to find the eigenvalue, use the determinants method of the Hadamard gate matrix. So you just do this. This is the equation that you need to put in cheat sheet. And then you do this one multiply this one minus this one multiply this one. Then eventually you get lambda equal plus minus 1. Turn out to be the same as sigma C, sigma X, and sigma Y. Okay? And then you are asked to construct the tensor product of S and H, right? S is given by this 1, 0, 0, I, and H is the Hadamard gate. So again, how do you do tensor product? This 1, right? This 1 multiply the whole thing. This I multiply the whole thing. And then 0 multiply the whole thing. Then you get the tensor product. Okay? And then I ask whether this is Hermitian. Many of you know how to do it. Just apply the Hermitian, the self-adjoint matrix, so which is the complex conjugate followed by transpose. Yes, very good. So if you do it, basically you see that if I do transpose, right, you look at this diagonal. You do transpose, actually it is the same. The matrix is symmetric, right? But then after that, you apply complex conjugate, all this I got changed. So they are not the same. So that's why it's not Hermitian. Okay. And then I ask whether they are unitary. The easiest method is to do a multiply to itself its adjoint matrix. You just go through the math, you find it is, right? Some of you just try to multiply 2 columns to show that it is orthogonal. That is not enough. If you want, you can also say that because S is unitary, H is unitary, so their tensor product must be unitary also. Okay, so that is also okay. Okay, so any questions regarding this? I know it's very simple, but not all of you get full score. Some actually did not that well. So please practice more, okay? Now for this second question, it is actually more like pretty simple also, right? So, but then someone did ask me during the exam, right, which C0 gate you should use. But let's go through step by step. First of all, I want to find out the matrix that represents this circuit. So again, the circuits go from left to right because the input is on the left, right? The output is on the right. But when you do matrix multiplication, it goes from right to left, right? When you do matrix multiplication on a vector. So that's why this one corresponds to this one. This one is this one, and this one is this one, right? So the first one is I tensor product H, because I already told you this is the IBM convention. The MSB is at the bottom, the LSB is on top. That's why you put I in front, I tensor product H. Then you have a swap gate I gave you already. You also have a C0 gate I gave you also. Okay. Then you do tensor product for I and H. You just, I again is 1, right? So 1, you put H here, another 1 put here. This is 0. 0 times H is 0. That's how you do the tensor product. Do not forget 1 over square root 2. Now, how about the C0 gate? Can someone tell me? Someone was asking, right, in the exam. Isn't that C0 gate is this one? Sorry. Say again. Oh, you cannot see it. Okay, sorry. There's some problem. So I write it here. 1 0 0 0 0 1 0 0 0 0 0 1 0 0 1 0. Right? Why not this one? What's the difference between the C notes I gave you and this one? Yeah. Right. But yeah, that is because this one, the control QB is the MSB, the one I just wrote. Here I gave you the control QB is the LSB. So in this circuit, because the control QB is on top, which is LSB, that's why you should use this matrix, right? So remember this. And we actually did that before when we tried to implement the swap gate using C0 gates, remember? So then the rest is just matrix multiplication. Let's do not spend time on this. Then eventually you get this, right? So again, the whole circuit, any quantum circuit at the end is just a matrix multiplication, unless you have measurement. Then the second question is, what if the input is 0, 0? What is the output? I ask you to use matrix multiplication. Then all you need to do is, again, come up with this vector. This means I have 1 component of 0, 0, 0 components of 0, 1, 1 component of 1, 0, and then, 0 component of 1, 0, thank you. And then 0 components of 1, 1, right? Although simple, I really hope that you know this very well. This is 1, 0, 0 plus 0, 0, 1 plus 0, 1, 0 plus 0, 1, 1. This is exactly what this column is about. Yeah. No, we still do this because we always put, when we write this, MSB is on the left. Yeah, that is only for graph, right? So this is still so-called little endian, right? If you do what you did, then it becomes the LSB on the left and MSB on the right. That is the big endian. So I think PennyLink, have you tried that? That is another platform. They use big endians, if I'm correct. Okay, so in that case, you write that, but then you need to change the matrix accordingly, right? But here, we are still using little endians, and we keep emphasizing IBM convention just to show that when you draw the circuits, the bottom is MSB. But the way you write it is still MSB on the left because it's the little endian convention. Make sense? Yeah, good. So, yeah, then you just do matrix multiplication. Multiplication is easy, right? And you should realize that this is like a filter. Or what you do, because you only have 1 at the top, you just take the first column. I think about that. Sometimes you can think about filter, like the graphics, image processing. It's just like a filter, a convolutional neural network. Yeah, all these things, right? Now, this is matrix multiplication. Then I ask you to use bracket with reasoning, right? Because very often it's easier to understand, and also you can derive an algorithm by using this much easier than doing matrix multiplication. So I write down what we already wrote in part A. C0 gate at the right, swap gate, and then I tensor product H. Then the first thing is that you apply I tensor product H into 0, 0. And you should know right away, okay, this is tensor product, so it is not entangled, the gate, so I can just apply I to the first qubit 0, so I get 0. And then apply H to the second qubit, the least significant bit, right? So I get 1 over square root 2, 0 plus 1. That's what Hadamard gate does. It does the superposition. Is that okay? And because of this, then I can write this, and then I just do multiplication, right? Because again, this is nothing but just a tensor product. I can distribute it. Then I get 1 over square root 2, 0, 0 plus 0, 1. Then I apply swap gates. By the definition of swap gate, is swap the index inside the basis. 0, 0 is still 0, 0. But 0, 1 becomes 1, 0. That is the definition. Right? You even don't need to think about that. And then we apply control NOT gate to it. Again, we can do distribution, apply control NOT gate to 0, 0. Now, what is the controlling qubit in our case again? I mean, LSB, right? So we look at this. This is the control qubit. It's 0, so we do nothing. It's still 0, 0. When I apply C0 gate to the second one, the control qubit is again 0. Okay, if you thought it is the regular one, then you are going to do something, right? But no, the target qubit is the most significant. So that's why 1, 0 is not changed in this case. So as a result, you get 1 over square root 0, 0 plus 1, 0. Now you check against what you did for the matrix multiplication. Again, this is what? 0, 0. This is 1, 0. Right? So it is correct. Oh, let me do something like that. Okay, so it's correct. The same, right? So these are the skills I want you to learn and be very good at in this class, right? Although, because if you know this well, you find that the algorithm I have been teaching is also easy to understand. Like the Shor's algorithm, we always use this concept. So try to learn this well. So the midterm is not difficult. Okay, maybe my recording died. Yeah, still one more. This one, somehow, many of you did not do it well. So what I am trying to ask is that, okay, I want to find the transform matrix from sigma z basis to sigma x eigenbasis. So what does it mean? Sigma z eigenbasis means that I have the basis formed by 0 and 1, because 0 and 1 are the eigenvalue of sigma z. Sigma x eigenbasis are the basis formed by plus and minus, because plus and minus are the eigenbasis of sigma x. So I want you first to form the transformation matrix that I can transform a vector which was represented in the sigma z eigenbasis to be represented in the sigma x eigenbasis. Right? If you forgot, remember we have a fake but correct example. If you treat this as plus, right? If I have a vector here, V, it can be represented as a linear combination of 0 and 1, or a linear combination of plus and minus. You can go through the trigonometry, pretty complicated. But when you go to a space that you cannot visualize, you better use the matrix. And the matrix for converting them is this. The element is the ket of the new basis. Inner product with the is the bra of the new basis. Inner product with the ket of the new old basis. Okay. So what do I mean? For example, this is the, you can call it either 0 or 1. Let's start with 1, right? Maybe easier. The first. This is the first row and first column, right? Both are first. So what is this? It is the first basis of the new basis, first basis vector of the new basis, which is plus. Inner product with the first basis of the old basis, which is 0. That's why I have plus inner product with 0. How about this term? It is the first basis of the new basis, so it is plus. Inner product with the second basis of the old basis, second basis vector of the old basis, which is 1. Is that okay? Right? Because I'm claiming that the first basis vector of the sigma c is 0. The second one is 1. Then the first basis of the sigma x is plus. The second one is minus. So what I'm doing is that based on the row and column, the row will take the bra of the new basis, right? The correspond to that row. So for example, this one, it is the second row. Yeah, very good. Second row and second column, right? So you take the second basis vector of the new one, which is minus, inner product with the second vector of the old one, which is 1. Okay? So this equation you need to memorize or make it very clear in your cheat sheet. I don't want you to memorize, but it's easy to memorize, right? Because I don't have cheat sheet. Why I remember? Because I remember by this row and column, right? Then all you need to do is just to do the inner product. So I will start with what is plus? We know plus is 1 over square root 2, 0 plus 1, right? The reason I want to do that is because I want to do some multiplication. So I plug in, but plus this is a bra, so I need to make it into bra. So you have 0. This 0 comes from the old basis. Multiply from the right. So that's why you have 0 inner product with 0 and 1 inner product with 0. Similarly, this one. Let me just spell it out. Maybe it will be easier. This is equal to what? 1 over square root 2. Because it's plus, so it is 0 plus 1. The whole thing inner product with 1. Right? And that's why we have 0 inner product with 1, because this 0 inner product with 1, and then 1 inner product with 1, the second term, 1 inner product with 1. Okay? We do the same thing, but the good thing is, again, what? It's orthonormal. 0 inner product 0 is 1. 1 inner product 0 is 1. But 1 inner product 0 or 0 inner product is 0. They are orthogonal to each other. Right? So as a result, the first term give me 1. This term give me 1, 1. And this one give me negative 1 because it was negative inner product with 1. I have a negative sign here. Right? And then you realize that, hey, the transformation matrix turned out to be H. Okay? And then I ask you, now transform this given matrix from sigma C to sigma X. So this matrix is written using the sigma C eigenbasis, which is Hadamard gate. So how do you transform it? If you remember, the equation is that we transform any matrix to a new basis. You just apply the transformation matrix on the left and is adjoint on the right to that matrix. Okay? So you can go through the math, but now we realize that U is actually H. So what we are trying to calculate is H dagger. But H times H is what? H times H dagger is what? 1, right? This one gives me identity, right? If you remember, if you don't remember, just do the matrix multiplication. So it's H itself. So this is a pretty interesting thing. The transformation matrix is the Hadamard gate. Yeah. After all this, adjust the calculation, right? Just do substitution. I do want you to make this very clear how to do the transformation matrix. This is very useful, right, in many areas, and is also called similarity transformation. Yeah. What is project? Say again, project. Yes, you can say it's a projection matrix. You're correct in that sense, yes. Because what you're doing is not really projection, is that you find out this row, the first row, try to find out all the component of this O matrix, the O vector. The projection of the O vector components onto the first component of the new matrix. You're right. This is transform matrix. But the assignment, the projection matrix, that was projection operator. We try to project to one vector. Here is not. Here we're actually transforming, but I just think that, yes, you're right. What it's doing is to project all these components to each component in the new basis. But that one is only project to an arbitrary vector. I want to project a vector to an arbitrary vector, then I use this projection matrix, right? But this is still transform matrix. Okay, great. Okay, so we'll stop here if no more questions.